Welcome to this explainer. Today, we're diving into the absolute ultimate engineering showdown of spaceflight. I mean, we all look up at these massive rockets tearing through the atmosphere, right? But what's actually powering them? Well, it all comes down to two major types of rocket propellants, battling it out to conquer gravity. Think about it for a second. How exactly do you put the brakes on a rocket flying at thousands of miles per hour? Or how do you steer it perfectly into a super narrow orbit around another planet? To really understand how we control a spacecraft, we first have to understand the incredibly powerful explosive chemistry pushing it upward. All right, let's get our fundamentals down. What is a propellant? Simply put, it's the chemical substance used in rocket engines to produce thrust. Basically, it's a very specific mix of a fuel and an oxidizer. When these two combine inside a combustion chamber, they burn and rapidly eject extremely high-speed, high-pressure gases out of a nozzle. And that physical action? That is exactly what pushes the rocket to the stars. Let's meet our first competitor. Contender 1, solid propellants representing unstoppable power. So we classify propellants into two broad categories based on their physical state. Solid propellants are the unstoppable brute force powerhouses of the aerospace world. It helps to think of a solid rocket motor exactly like a giant, highly engineered firecracker. The fuel and the oxidizer, they're already premixed together into a single, homogeneous, solid grain right inside the motor casing. You've got an igniter, some insulation, and a nozzle. But here is the massive catch. Once you ignite it, combustion starts on the exposed surface of that grain, and it just burns continuously until every last bit of it is completely consumed. There is literally no stopping it once you light that fuse. Now, the specific chemistry inside these solid grains is actually super fascinating. We generally break them down into two main types. First up, we've got homogeneous or double-base propellants. These use chemicals like nitroglycerin and nitrocellulose, and they're typically used for smaller rocket motors and missiles. Then you have composite propellants. These use separate particles, so something like ammonium perchlorate for the oxidizer and aluminum powder for the fuel, and it's all held tightly together by a polymer binder. These composite mixes are your real heavy-duty materials. They're exactly what we use to get massive, modern launch vehicles off the pad. Which brings us to the crucial point, the massive engineering trade-off. On the pro side, solid propellants offer this incredibly high thrust right at ignition. They have a really simple construction, they're easy to store, they have a fantastic shelf life, and they are incredibly reliable with almost no maintenance. But look at the cons. You cannot throttle them, you can't shut them down, and you definitely can't restart them. You basically have zero control over the thrust profile once it's lit. Plus, they generally have a lower specific impulse, which is just how rocket engineers measure efficiency, at least when compared to our next contender. Because they deliver instant, guaranteed power even after just sitting in storage for years, solid propellants have some very specific, ideal applications. They are absolutely perfect for heavy liftoff booster stages, ballistic missiles, sounding rockets, and, this is a big one, escape systems for crewed spacecraft. In those situations, instant, fail-safe reliability is quite literally a matter of life and death. Moving on to Contender 2, liquid propellants, representing precision control. If solid motors are the brute force sledgehammers, liquid systems are the highly complex precision instruments of spaceflight. Instead of a pre-mixed solid grain, a liquid rocket engine stores the fuel and the oxidizer completely separately in different tanks. When it's time to fire, you have this incredibly complex feed system and high-powered pumps that force the liquids down into a combustion chamber, they mix, they ignite, and they eject those high-temperature gases. It's a lot like the gas pedal in your car. These feed systems allow engineers to control exactly how much propellant enters the chamber at any given millisecond. And just like solids, liquid propellants come in different flavors, usually based on how they ignite. The two big ones are hypergolic and cryogenic. Hypergolic propellants, like UDMH fuel and nitrogen tetroxide, are amazing because they ignite spontaneously the absolute second they touch each other. No spark needed. This makes them incredibly reliable for attitude control and maneuvering out in the vacuum of space. On the flip side, cryogenic propellants, like liquid hydrogen and liquid oxygen, have to be stored at mind-numbingly cold temperatures. They're a massive pain to handle, but man, they produce the absolute highest specific impulse among chemical rockets. So, here is the flip side of our showdown. With liquid propellants, you get total dynamic control. You get higher propulsion efficiency. You can throttle the engine up or down to adjust your speed, and, get this, you can actually shut it down and restart it in space. But You pay a massive price for that capability. The engine design is vastly more complex, the manufacturing costs go way up, and storing those cryogenic liquids is a huge logistical headache that requires some seriously long launch prep times. However, that precise throttle control, the efficiency, and that restart capability make liquid engines absolutely essential for the delicate, prolonged tasks of spaceflight. We rely entirely on them for the upper stages of satellite launch vehicles, for hitting a precise orbital insertion, for human spaceflight missions, and for steering spacecraft on those really long lunar and deep space planetary missions. Section 3, the head-to-head showdown. Ultimately, this whole thing boils down to a fundamental engineering compromise. Just look at the stark differences here. Solid propellants are wonderfully simple to build and super easy to store, but thrust control and restart capability? Totally out of the question. Liquid propellants give you that magical throttle control and the ability to restart, but they are incredibly complex to build and famously difficult to store, especially when dealing with extreme cryogenic temperatures. Let's break down the efficiency battle. If fuel efficiency is your #1 goal, which, again, engineers measure as specific impulse, liquid propellants win, hands down. They provide a much higher specific impulse, which just means better overall propulsion efficiency. This is a real game changer because it allows you to carry heavier payloads much further into space for every single pound of propellant you have on board. But hey, it's not always just about efficiency, right? It's also about readiness. If your mission requires you to launch right now on a moment's notice, like with a military application or an emergency escape system, the solid propellant takes the prize every single time. Liquid systems, with all their complex pumps and extreme temperature needs, just demand way too much preparation and fueling time on the launch pad. Finally, let's talk about the perfect launch team. So at this point, you're probably asking, which one actually wins? Who is the ultimate champion here? Well, here is the big plot twist of our propellant showdown. They aren't actually enemies at all. They're the perfect launch team. Modern launch vehicles almost always use a synergy of both technologies to take advantage of their unique strengths. Engineers will strap solid rocket boosters to the side of the rocket to conquer gravity and get that massive immediate liftoff thrust right off the pad. Then, once the vehicle is moving and it sheds some weight, they switch over to the liquid engines in the core and upper stages for that precise throttle control and orbital guidance. Because every single space mission is basically a giant, complex puzzle. As the source material puts it so perfectly, the selection of the appropriate propellant system is a crucial decision in launch vehicle and spacecraft design. Engineers have to perfectly balance the raw, simple power of solids with the highly efficient, precise control of liquids if we're gonna make it to the stars safely. It's all about picking the right tool for the exact phase of the journey. Which leaves us with a final thought for today's explainer. As we look to the future, planning these incredibly complex, long-duration missions to Mars and deep space, which propellant technology will evolve to conquer the next frontier? Will we figure out a way to make high-efficiency liquids easier to store for years in deep space? Or will we invent an entirely new way to control the burn of a solid? It's something to think about. Thanks for tuning in, and keep looking up.